Hi all, welcome to my channel. Today I am going to explain you the LRU cache. This is the most important question in any of the interviews. So in my past around 10 interviews, right? I think it's almost in 8 interviews they asked me about LRU cache, especially this kind of LRU cache. This kind of problem statement will basically ask in the second round or third round of interviews in the technical rounds. So before going to explain the LLU cache, right? So it's just a quick update. So I was consistently updating the low-level designing videos, like especially machine coding rounds, which is generally asking nowadays, like any of the companies, big companies, and also I have recently started the my interview experiences. It's from past 3 months. I keep on giving the interviews for senior software engineer role. So where I have encountered almost 50 plus of interview questions. So this is one interview which I shared about what are the relational database questions which I asked. So if you missed the video, I'll put the link in description. You guys can watch those video. And yeah, this is about low level designing. And in this system, in this SD interview series, in future I'm going to upload my other interview experiences also, like how I got cracked some good companies they offer very good, and how I cracked like Java, and also how I cracked coding interview questions. And also I also share all my rejections where I, due to some silly mistakes or some mistakes, it got rejected me in final rounds, which I'm going to share everything in the SD interview series, which might help to any person who are appearing to those companies. So without any further ado, let's start the LRU cache. So basically, when this cache comes into picture, right? So in our services, so when we are designing any systems, right? We have some applications is there. We have number of microservices are there, and we have some gateway is there, and we have some front end is there. Yeah. So front end basically ask request to our backend services, right? So for the backend we have gateway is there. So gateway is responsible to redirect to route it to respective microservices. Let's say in Amazon, right? It may be cart service, or it may be user service, or it may be item service. So whatever service is there, depending upon the user query, the gateway is responsible to route it to respective microservices. So let's see, like when we talk about scale, right? So when we talk about Amazon, or like any kind of e-commerce applications, or let's comes to any applications which is basically user centric, which is like it's like huge amount of data is consistently coming, like talking to our systems. So every time, so this card service has dedicated DB is there, like MySQL or any SQL DB, depending upon our microservice use case. Either it can be MongoDB, or it can be NoSQL, or it can be SQL DB. So in a traditional microservice architecture, each service has its dedicated DB, and each DB has like many tables are there. But every time whenever request comes, if you want to talk to the DB, right, it will add the extra latency. First of all, let's say for a single request, to serve a single request, let's say we are taking 1 second, but in that DB latency is taking around 500 milliseconds. So let's say 1,000 customers keep on asking only 5 records, five unique records. So if this is the picture, right? So something we can do to decrease this latency, like let's say user 1 will ask the record 1, so we take it from DB and serve to the user. Similarly, user 2 asks the record 2, and user 3 asks if user 3 asks record 1, right, instead of asking from a DB, right, we can save this 500 milliseconds. Somehow we need to skip the DB call. So that we can, because user 1 is already asked, so it is already recent record, right? Somehow we need to store this particular record in our service, or at some different microservice, where instead of again calling DB, right, we can directly call to the particular function to return the particular data. There comes to that is nothing but a simple cache. Like caching the DB records in the service itself to reduce the DB calls, so that our system can easily scale to larger extent, and system can easily serve with very low latency. So instead of taking 1 second, it will take only 500 milliseconds per request. Yeah, let's say 1 second. Yeah. So let's see where we can put the cache. Like so our main goal is like to stop talking to DB for already read records from DB. That is our first goal, right? And so there is some disadvantage also will be there with the using of cache, because we can maintain some cache over here, in memory cache. Let's say we can store the data in hash map itself, a key comma value pair, or we can have some distributed cache where it will help during horizontal scaling. So when we do because of huge load, right, we will do horizontal scaling, like we'll increase the instances of each services. So the service one will become 3 services. Service 1 will become 3 services, and service 2, depending on the load, we'll auto scale the services. Like either we increase, if there is no load, either we will decrease the instances. So that if using distributed cache, right? So with the help of single cache itself, we can maintain complete data, and we can serve. But if you're using in-memory cache, right? So each instance has its own cache. Depending upon our gateway routed, right, either it can be cache hit or cache miss. So it might chances of like duplicate records will be there in the each instances, but it's okay if you are okay with in-memory caching. If you are using distributed cache, right, for all these microservices, for all these instances, only single cache, and then it's guaranteed that that record is only stored at only once in the distributed cache. So this completely depend on our load balancer, basically our load balancer technique. So this is altogether as a separate topic, which we will discuss in later videos. This basically has some sticky session or else a round robin fashion. Load balancer will be responsible to distribute the data to all the services evenly. So with the help of some algorithms, which we can discuss later. As of now, our topic is like LRU cache, right? So what is LRU? Now we understand what is cache, like storing the DB records inside the hash map itself, which is like to stop the intervention of DB every time whenever user queries. So let's say if you keep on adding the records inside the hash map, right? Which itself make hash map is very huge in a short period of time, which itself makes this complete service itself like a memory out of exception. And also hash map becomes very overloaded, and it loses its algorithm, like serving the data in order of one, because hash map will basically, when it comes to Amitab's complexity, hash map will be basically insertion, updation, accessing the data is like order of one, right? So that by default itself will become lost because of huge data. There will be a lot of collisions maybe happened. So a hash map will keep on adding the bucket link, keep on listing those values in a bucket. So which makes the hash map very heavy, and also which is impacting to the service itself, because we're storing too much of data inside the service itself. Because microservice itself should be very lightweighted, right? That's where we come the picture of LRU. So this LRU is nothing but so if you talk about LRU, right? So let's say 1 second. Yeah, this LRU is nothing but it's a eviction policy. Nothing but we need to evict the data in a cache such a way that all the recently request users it cannot be stored in a cache like for a long time. So let's say we are taking a data store. We're taking some data where at max we can store only 100 records, because we are limiting ourselves to 100 records, so that cache will perform very efficiently, and cache will not become overloaded, and also this shouldn't impact our service or microservice. That's why we constrain the number of records in a cache is equals to 100. So let's say we will store cache. Let's say we'll store record. Okay, record 1, record 2, and so on up to 100 records. Let's say in future, right? Okay, instead of viewing like this, right? You can view like this, like. So this is, let's say, assume this is a queue. First we'll check the request from request is present in cache or not. If request is present not in a cache, we'll query the DB. We'll get the data. Once we get the data, we'll put it in queue. Let's say this is head and this is tail, right? We'll put it in queue. Basically, we'll put it in hash map. Let's say this has a queue. So we put the record 1. So in future, right? Some person will came. He asked another record. So that is not again present in a cache. This time we need to fetch the data from DB, and we'll add the record over here. When compared to these two, right? Which is the most recently used one? R2, and which is the least recently used one? R1. Likewise, all the records will keep on appending. Once complete cache size got full, right? So there, if suppose a new request came, if suppose the particular request is not there in our DB, in our cache, then we need to query the particular record from DB, and all the least recent used records will be at the tail, right? So likewise, it will append like this. These are like least recently used one. So we remove the record from tail, which makes n equals to 100 to 99, and we add the newly record into the first value. Let's say R101, and we remove the R100, which is like least recently used one. So let's say someone query the data someone query some particular record which is already presented inside the cache. Then what we do? First, we remove the particular record from the list, and because that record is nothing but most recently used one, right? So we remove the record over here and we add the record at the front. So which means that this God has higher priority because someone is keep on searching the query, keep on searching the record which is already presented in our cache. We are removing that record from there, and we are inserting over here. This is the simple funda of like how LRU cache will work. There are many cache eviction policies are there. Like LRU, least recently used one. We are removing the least recently used one, and something called we have another cache eviction policy called LFU. Nothing but least frequently used one, which is nothing but this is a separate topic we can discuss later. But this is not mostly used in industry. We have a hash map is there. Let's say record 1, which is used around 10 times. Let's say record 2, which is used around 5 times. Record 3, which is used around 10 times. Let's say we have capacity is only 3. We can only store 3 records in a cache. And let's say a new request came. Let's say R4, record 4. When compared to these 3, right, which is the least frequency. When it comes to frequency, 5 is the least frequent one, right? So we need to remove this 5. R2 value, and we need to insert into the hash map. R4 is 1. Likewise, we can maintain the frequencies of all the hits of particular record as a hash map in the key comma value pair. Whichever is like least frequently used one, we can remove that. We can remove the particular value. So this is a bit complex algorithm when compared to LRU because this frequency is nothing but these frequencies are key. Let's say we have a hash map is there. Let's say this is the 1, 2, and 3. These are nothing but frequencies. So and we need to take another hash map. In that hash map, we need to store the record and we need to store the frequency, right? R2 record and we need to store the frequency 2 times, 5 times. But here we can store R1. This is the R1. And same another frequency will got R2 at only single frequency. But let's say R2 got another hit, right? First we need to take what is the frequency existing, which is nothing but let's say 1 will be there, and we need to remove that. We need to find the R2 element and we need to remove the particular R2 value, and we need to update this 2 and we need to insert the R2 over here. Likewise, we need to maintain a frequencies as a key value and records as a key value. 2 hash maps we can achieve the LFU, but this is not frequently used algorithm in the industry. This may be used in some kind of problem statements, but most recently used algorithm is like LRU. Nothing but whatever we discussed as till now. Like this is the least recently used. So let's discuss about how can we implement this LRU with the data structures available in Java or in any programming language. So while discussing both about two things, one is like mandatory, nothing but a hash map. Hash map will store the key comma value, right? Yeah, this is mandatory. Second thing is like somehow we need to store the keys. Nothing but if you have something called linked list, right? So 1 second. Yeah, we have linked list. Yeah, we have an address of 1 and 2, and we have an address of 2. We have 3 and null is there, right? So if you have keys in a linked list fashion, we can easily keep track the keys, and we can remove the keys and adding so by seeing this one, you can clearly observe, right? By seeing the above algorithm, we can say like, okay, either we need to insert at beginning. Whenever the cache hit coming, we need to remove that particular value, and we need to again insert at beginning, right? So this is the simple funda of LRU. So which means clearly says that, and also whenever cache eviction cache like size got exceeded, right? We need to remove the data from rare, like nothing but tail value, which comes to modify the linked list into AA linked list. So we can use AA linked list. So which will keep track all the keys, which will serve like insertion, updation, and deletion, insertion, removal, insertion, update, removal, and also insertion and removal will be done in the order of 1 operation. Here like get and put will be done in the order of 1 operation. So in in order of 1 operation itself, we can achieve this LRU implementation. So let's say so if you don't know about LRU, if you don't know about using AA linked list or hash map, right? First think about because hash map is a basic thing. If any good engineer will get in mind, like whenever you want to store the values in memory. So then you can use the linked list, which makes the order of n is the to remove the keys. Then interviewer ask you to improve. Then you can think of like, okay, what if I get in order of 1, so that we can why it's taking order of n means because linked list will only store the key comma at next address, right? It will not store the previous address. If somehow we store the previous address, we can simply access the particular record directly instead of accessing from beginning to ending. So that's where we can optimize from order of n to order of 1. So some more advanced, some senior engineers, right? So we can directly say, okay, we can use the linked hash map. So we have linked hash map is a kind of data structure which is present in the Java, where without implementing the AA linked list or without it itself take care about removing the least recently used records depending upon the specified size we mentioned. So without any further ado, let's quickly see the code and we can understand even more better. I'm going to explain 3 ways. One is like with the help of singly linked list. Second is like with the help of AA linked list, and with the help of linked hash map. So let's talk about singly linked list. So these are like generics k comma v, and you can mention if you want your cache to be constrained to only integers, right? You can mention integers, but I am giving more flexibility depending upon whatever we have passed over here, right? That will become as a data types for k and v. So we initialize a singly linked list which will keep track all the keys, and we are maintaining a hash map where it has all the key comma value pairs, and we also will declare the max size which a user is going to define what is the maximum size of a capacity. I am declaring here 3. So whatever I just told, right? So during put operation, right? First we'll check, okay, if it is already contains. If we already contain, put means nothing but overriding. If it already contains, we just override. Before overriding, we first, because that key is most recently used, right? we remove the key from the record from the linked list, which will take the order of n operation. And also we can put the data and we can put the particular record in the hash map, and same as add first. We'll use add first, which is nothing but insert at the beginning of the particular key. If let's say if cache is exceeded the max size, right? First we'll remove the last value, and we take the removed value and we remove the value from the cache. So simple thing. So only drawback is like removing the key. It is taking order of an operation, right? So next thing is the get query. Get also same thing. If it is already contains, first we remove the particular one which is at somewhere at the middle of the linked list, which will take the order of an operation, and we'll add it first. So if it is not contains, it will return null. If it is contained, it will return the value. Similarly, for removing, it's like same thing. Like if you are removing a record from the hash map, and at the same time we remove the particular record from the linked list itself, which is also taking order of n. So with the help of singly linked list, right? So we cannot optimize to order of 1 even though we have hash map, because we need to remove the values, right? Or remove insertion will take order of n. So we can optimize something with the help of using the double linked list. So I have declared a node, list node, where we have like previous and next values are there. Previous value store the previous address, and next value will store the next address, and we have LRU cache is there. So I'm declaring the two nodes, head and tail. Tail will remove the tail will have the most recently used one. Head will have the least recently used one. So head, and also I'm declaring the maximum capacity. First initially I'm declaring the capacity, and also I'm initializing the hash map. Then when it comes to put, right, let's say put, if map dot contains key, right, first is like we take the value, first we remove the node. Here we have the address is there already. Because of that one, we don't need to keep track we don't need to iterate from 0 to n, right? 0 to particular value. We can directly simply, because T will have like a previous address and next address, we can simply do something like n.preview.next equals to n.next. So which will basically take in the value of temporary removal 1, and n.preview will give the previous value, previous node, and in that next address location we are modifying this temporary dot next address location, so that we can easily unlink the particular value, a particular value from our double linked list. So same thing happening, removing node. Suppose if n dot this condition only happens if n dot preview not equals to null. Which is nothing but the particular data is not head. If it is a head, right, we can simply make it as head equals to n dot next, and we can remove it. So we can remove that n dot next dot preview equals to n dot preview. So if you see here, right, so t dot next, if the particular value is not at the ending, right, which means a particular value at somewhere at the middle of the data. I'll explain 1 second. So just understand the remove node, how remove node will perform. 1 second. So we have values are there, keys 1, 2, 3. Let's assume we have address 1, and we have address 1. We have address 2, right? The next address, and this has the previous address, and address 3 and address 2. Yeah, likewise we have, and it has null. But this is the head, and this is the tail. Let's say I want to remove the value of 2. Let's see how let's see how we can do with the help of code. We can see the code. So we can remove the n, right? So n is 2. So n previous we have a1, and next we have a3. So n previous is not equals to null. N previous is not equals to null. So we simply n dot previous is nothing but this a1, right? So So here we are modifying, this will modify as like n dot previous dot next. So in this next location we will modifying with the n dot next a3. So which means this will directly link it to the a3. You got it right? This will directly link it to the a3. Yeah, suppose and also we need to check, right, if n dot next, if this is not equals to null, which means this means a3, right? Here n dot next is not equals to null, so n dot next nothing but a3 dot preview, we should modify the n dot preview nothing but a1. So this will be modified as a1. So this means this particular node is like completely unlinked with the in between. So these two, like from this doubly linked list, this node is like unlinked. So likewise we can do in an order of one operation itself. So similarly for we can insert the same record at the beginning or insert the same record at ending with the help of this code itself. Yeah. Next thing is like offering the node. Offering is nothing but inserting at the ending, like because in this particular program I'm keep tracking the most recently used at ending, and the least recently used at like head we need to remove. So if tail is not equals to null, tail dot next equals to n. If head is null, right, make it as the tail as a head. So this is nothing but just a allocation, like this is nothing but this helps to form a chain. So n dot preview, I think these things you guys understand, right? So so let's say we got one particular record. Let's say we got a record 5 and some address null, right, initially. So we'll check, okay, we have some linked list is already presented, right? So tail not equals to null, condition is right, and tail dot next, so we are adding over here, we are adding tail dot next equals to n. So we are linking over here, which means this is the most recently used one, and this is the next most recently used one, this is the least recently used one. Tail dot next equals to n. Now we need to modify the tail dot preview, right? Tail dot preview we need to modify the tail value, actual tail value, and tail dot next is actually null, and we're making this as a tail. Head is not equal to null means we don't need to make anything. If this is the only record presented, right, we need to make a head as a tail. So likewise we can offer so which means that tails will have the most recently used one, and heads will have the least recently used one. So which is guaranteed, like by seeing these operations we can access, right, order of one in both insertion and removal, right? Because this is the advantage of using double linked list. Yeah. So same thing happened. Put is like first remove that node and add the node to the most recent side. So same thing, if max cap is greater than, right, remove from the cache and remove the node. And also we're adding at the tail, and same thing we're adding back. During get also, I think same thing will be there. Just remove the node and also offer the node. Just whatever we just written in the singly linked list, right? Same thing we are written with the help of doubly linked list. So let's execute. So these are the driver functions. These are the driver. Okay, these are the driver functions. So we can understand with the example. Let's say, let's say, okay, sorry. Let's say we have we first inserted C++ in the first record. Then inserted Java, then inserted Python. Here we are asking to get the data, to get 1. So this is a cache hit, right? We are removing the record and adding at the most recent side. Okay, so we'll return the value as like C++, and again we inserted Golang, and we are asking get off to, which is like most recently. This will be removed over here, and this will be added over here. Java. And next thing is like we're adding one second, sorry, because our max size is only capped to 3 elements, right? we cannot add the Golang over here. What we do is like first we remove this value. This is the tail value. We remove over here and we added Golang over here. So similarly, let's say you have let's say we are including Spring over here. So Python is there, which is like tail one. We remove the Python and we added the Spring. Still the one value is already existed because this is not end, right? So when we ask the get of one, we'll get the C++. Here we get the null, right? Yeah. And again we inserted the 5, so now we inserted in the 5, but here the 1 is like least recent user, right? So 1 will be removed. So in the 5, fast API will be included. And we're querying the, yeah, if you query the get of 1, right, you will get null. If you query the get of 4, right, okay, here when we access the get of 1, right, the C++ will be deleted over here and C++ will be added over here. And then we're including fast API. While including the fast API, this is the least recent user one, we remove the Golang. So which means which left the values are like Spring, C++ and fast API. That's why when we query the cache or get of 4, right, nothing but 4 Golang, right, we are getting the null value. So this is the proper implementation of LRU cache. We can discuss even more better approach. We no need to write all this heavy code. Like we no need to implement double linked list or single linked list. Directly what we call like in Java, right? We have something called a linked hash map. So this is the combination of linked list plus hash map. Here we maintain the access order is true. Here we are overriding the one function from the linked hash map instance called remove eldest entry. If you mention the size, right, so whatever the linked list size is there at that particular amount of time, if the size is greater than the capacity, it will automatically remove the value. So that's why we just no need to keep track, no need to remove the value, like every time you want to remove first, remove the value, add first, remove last. These things are not required. By default, it will remove the value, the eldest entry, remove the eldest entry. We can directly simply access like cache.put and cache.get.default and cache.remove. That's it. So this is like more advanced version, but in interviews, right, first try to come up with if you don't know about double linked list, try to come up with single linked list. Then you can implement double linked list. But if you know, right, this particular linked hash map, implement with double linked list and then tell to the recruiter, okay, but in the Java we have some function called linked hash map, some data structure called linked hash map. By default, it will provide out of bound operations. We don't need to keep track anything. With the help of remove eldest entry, we can achieve the LRU cache. So yeah, this is the proper implementation of cache eviction, implementation of LRU, and yeah. So I think that's it for today's tutorial. Please subscribe to my channel. I'm consistently uploading the videos. If you like the video, please subscribe, like and share to your friends. Thanks. We'll meet very soon.